Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
Okay, so in our previous video tutorial, we started working with time series, and we specifically generated a time series for maximum temperatures or 12 o'clock daytime temperatures for my region of interest as a whole. And we started with some modeling in terms of generating a regression, simple, regression with times maximum temperatures as my dependent variable, my y variable, and two independent variables being a constant and being time. So we generated a constant and we generated a time series, and then we regressed that on our maximum temperatures, and we got a regression equation for each and every location within my region of interest. So we're going to continue with that. Just a quick recap. As I said, first of all, we generated our time series of our region of interest. There it sits. Okay, using this particular piece of script. And then we generated a linear trend or a regression model for our region of interest. And this is how that looks. And remember, we said we can use any of these locations. Let's say that specific location. If we press there, we will get the regression function for it. There it is, the trend. So the scale is the coefficient, the time coefficient, and the offset is the constant. Okay, so it assumes there's no error term, or the error term is undetermined here. So the time variable that we've calculated there, remember this is the time variable that we generated here, the time variable there from 1960, times this value plus the constant should give us the 27.1. And so that you can use now as a, let's say, to estimate future. If you know the time period, and you can just slot it in there, and then you can generate its estimated maximum temperatures on the assumption that the linear trend will continue, meaning the past is a perfect prediction of the future, and therefore the constant, the trend, the coefficient, the trend coefficient, time coefficient will not change. It will stay constant, and therefore maximum temperatures will just go, it will increase and increase by this factor, 0.0117 degrees per year. Okay, so that's roughly what it says. The temperatures will increase by 0.0017 degrees per, well, this is month, yeah, per month. Okay, so that is on a monthly basis, not a yearly basis, per month. So if we multiply that by 12, we'll get by how much it will increase per year. Okay, so we can also generate a chart for this. Okay, a chart for this, whereas this now indicates each and every single location. The chart, this one here, will indicate for the region as a whole, for a singular. So there will be one coefficient and one constant. So in this case, where we generated the image, this image here, we will get X amount of constants, X amount of time coefficients depending on the number of locations. But what we're going to do here is to generate one constant and one time coefficient for my region as a whole. Now that should basically be very similar to the individual locations constant and time coefficient. Anyway, let's have a look and see where we get to this. Okay, so I've generated a regression function for a simple regression function for my image as a whole. Okay, and remember this regression function is now a reducer of all 757 images. Okay, so just remember that it's a reducer. Okay, so let's go to the next one, and hopefully things will start becoming a little bit more clearer here. So now we're going to create a, okay, so sorry about reconcile it quickly. That's the beauty of staying in South Africa at the moment. We have something that is called load shedding. So periodically our electricity just goes off. And that was now scheduled for 12 o'clock. So we're going to have about a 2-hour load shedding now without power. So it's inverters and whatever kicking in. So I quickly had to just change the system so that I at least have a bit of power. Yeah, so that's load shedding for you. Anyway, so can't remember where we were before the load shedding started. But nonetheless, we're going to generate now a linear trend for my image, for my regression, for my region of interest as a whole. And it will be interesting to see what its coefficients looks like compared to the individual locations coefficients. Okay, nonetheless, okay, so let's go. So first of all, we generate our image collection. Okay, it's the same image collection as that we're working with. We're just giving it now another name. It's still scaled by that factor, and we add a timestamp. Now, I'll show you a little bit how this timestamp or the date stamp looks like. Okay, so now we've created the image collection, a dated image collection or timestamp image collection. We're going to create our variables. So first of all, we're going to add create this variable, which is called add variables, which will be my date variable. Okay, so which is this one here, my stamp, ID stamp, and which will then start from 1960 and count 1 month. Okay, so that would do that. And then I generate a constant. So I have a band here, which is my dependent variable, which is maximum temperatures. Then I have my year band. Okay, you'll see that that is my years. So you see there, the years is my time coefficient. Okay, and it's a float. Remember, all our variables we convert into floats, and we give it T. It's branded T. Okay, and then we have our constant. Okay, so we've got 3 variables here. We've got one dependent variable, which is maximum temperatures, and then we have 2 independent variables, which we labeled time, and a constant. And time is generated using this function. Okay, so there's our variables, and then we basically just add them all together. Okay, so we've got filtered, which is a data scale to G, and it's for our region of interest. Okay, so that's the data set, which is this one here. Okay, that's the data set for our region of interest, and then the 2 periods that we're looking, maximum and minimum period, which basically covers, and then we add our variables, all these things, our dependent variable and our 2 independent variables. Okay, so that's what we're basically doing here, and then we're just putting this on a chart, and specifically on a Chatters card. So we've got our UA chart.image.cs filtered, select, and then we select our dependent variable. In this case, maximum temperatures for my region of interest. It's a scatter. And we use the data set filtered, or the variable filtered. Now, as I said, filtered is my image collection with my variables clipped for this period. Okay, so that's what this filtered data set is. Okay, so that's filtered data set. And then I said we just select TMMX, which is our maximum temperatures as my dependent variable. These are just, making the chart a little bit pretty, give it a name, and obviously it adds a trend line. There's our trend line. Okay, so that's important. So it's giving our trend line. 0 is a trend line, 1 there's nothing. So play around with these numbers and see what the impacts are. Okay, you're welcome to do that. And then we just print the chart. And what we're going to get is something like this. Okay. So let's just confirm again. So first of all, I generate my image collection. Okay, scaled dated image collection for my clip. Scaled dated clipped image collection for my variable, dependent variable, which is maximum temperatures. Then I generate my variables that I'm going to use. And particularly, I'm going to use 2 independent variables, which is time, which is generated from 1960 on a monthly basis. And it's a float, and we name it T, and then a constant. Okay. And the constant, the algorithm will calculate itself. Remember, constant, what it says, a singular value, a value. Okay. Play around with the numbers, see what, if you leave that empty, what happens. And if you put a 1 there, it's basically just to say yes or no, whether it's a constant or not. Okay, then we just add all these things together into one variable, which is filtered, which is that image collection, with all these two other variables for clipped and for these dates. And then we just print the chart and print it. Okay, this is what we're getting. Okay, it's a chart like this. So let's make it a little bit bigger and see what it looks like. So it's got the time series as per our original time series that we calculated there. Okay, nothing different from these two variables, exactly the same, but now it has a linear trend. Now, unlike what we've done in RStudio, where it's a non-linear trend, you can see there's RStudio, it indicates a non-linear trend. We've basically just calculated a linear trend. And that's basically just see over time whether there's an increase or a decrease or a constant change. What's a long-term pattern, underlying structural long-term pattern of this particular time series. And this indicates an upward trend. Okay, so now we can download it. So if you go download, and this is where it's interesting, I can download it. I've already downloaded it. Okay, so I'll download it. You basically just press save to wherever. Okay, so there's the name. You can change the name and you save it. Okay, once you've saved it, let me just quickly minimize that and just rearrange my gentlemen. You'll see. Let me just quickly save this. Otherwise, it's gonna give me problems. I'll just leave it as a Excel workbook. Okay, so once I've downloaded it, you can open it and it will look something like this. Okay, so this is the download, the CSV file that I've just downloaded. Okay, so you'll see there it's in a CSV format. Now, obviously, I have to now convert it into Excel. So remember, how do you do that? You just highlight the whole thing. You go to data, you go to text to columns, you go to delimited, you go next, and you say comma. And you'll see it will split it. Okay, and you just press finish. You'll see now that it has also split the date, so that's easy. You can just move that now to where the data is, make that a new date, etc., etc. So let me not go there anymore. Okay, so that's how you now convert it into Excel. So what I've done in Excel, I've created this a little spreadsheet just to show you what the whole thing looks like. Okay, so what I've done is I've got my system date, which is basically just from 1 to so I'll just give it a number from 1 to 756. Okay, so I'll just give it a date. Okay, there's the date itself, January 1960, February 1960, etc. Now, what is important? What does Earth Engine do? Earth Engine, when it allocates this date, remember let's go to Earth Engine itself. When it says this, system start time and system end time. Okay, these two. It creates a float. Okay, remember we said they must create a float. There we go, a float. And what that basically does, it doesn't create the date as what we would normally say January, February, March. It creates a value. It creates a value. So this 21916 is the value of January 1960. Okay, so it allocates this value to the January 1960 image, this value here. It doesn't say 1960, January 1960, it gives you a value of 21916. Now, how do I get that? So if I simply just press on the date, remember this is now January 1960. If I right click on it, I go to format, where it's now in a date format. You see there, it's in the date format. You just go to number. And obviously just take the decimals way, and you see there's 21916. You press OK. You see, there it is. And then you can just do it for the rest as well. So this is what Google Earth Engine does when it does a date, a time frame for my images. It allocates a value, and that value corresponds to the appropriate date. But it doesn't give the date per se, like in a specific date format. Okay, so that's quite neat. So just remember that. And then obviously we have our actual temperature, we have our actual maximum temperatures. So the actual maximum temperature for January was 29.8, and okay, so and that values come from obviously from our time frame, our time series. Now, unfortunately, when you download this, you don't download the trend line. Okay, you can see there, you don't download the trend line. So if I download, let's just download it for instance sake. I'll save it and let's open it. Okay, so I've opened it. You see, it doesn't download the trend as well. It only downloads the date. You can see there the date, January 1, 1960, and the maximum temperatures. It doesn't download the trend line or anything else. Okay, but that's not an issue. We can work around that. Let me just close it. So we've got now our date, January 1960, but I've converted this date now into a value as what Google Earth Engine would do. Okay, I've got my maximum temperatures. Okay, so what we do now, how do I get the trend line? See, this is the trend line that I've generated. How do I get the trend line? Okay, so we go to our trend line. You see, if I click on any place on this one, okay, remember it's a linear function. So the two independent variables will be constant irrespective of where I am. Okay, so that's important to understand. So let's click on this one. You'll see, on this case, there is, and this is our April 2022. Let's make it in somewhere in the middle. Okay, so this is now for September 2015. You'll see the TMMX, remember that's our dependent variable, is equal to 5.776 E minus 5 times the system time start plus 22.618. Okay, so just remember those numbers, 5.776 E5 minus E5, 5.776 E minus 5, and 22.618. So if I go to another place on this linear function, you see exactly the same. So this is for 1975. The coefficient, the time coefficient, 5.776 E minus 5, and the constant 22.618. So those two coefficients are the same irrespective of where you are on the time series, simply because it's a linear function. So that should make sense. So I can take those numbers and plot it in Excel and generate my time series or my trend. Okay, so remember I start with the two coefficients, which is my time coefficient, that's 5776 E minus 5, and the 22.618. Okay, so let's make it a little bit bigger. So I plot my 5.776 value. So it's 5.776. Remember, that's the value there. Let's go back there. 5.776. And then there's E minus E5, meaning I have to divide that number by 5 zeros. Okay, so I have to take the 5.776 and I have to divide that number by 5 zeros. Remember, if it's a positive, then I will multiply it by 5 zeros. But here's a minus, so I have to divide it by 5 zeros. Okay, so that's what I do there. I take the 5.776 and I divide it by 1, 2, 3, 4, 5 zeros, meaning 100,000. Okay, so I've subtracted, so that value is the coefficient, the time coefficient. Remember, if I go back into our model, okay, our model, where it is now, this value there, that B1, that coefficient, B1 coefficient, that B1 coefficient in our case is 0.00000576. Okay, so that indicates the degrees Celsius per month that temperatures have increased and will continue to increase because it's a linear function per time. And then we've got the constant, which is 22.618. Let's go have a look again. Where's my constant? Where's my graph? See any place there? 22.618. There it sits. There it sits. Okay. So now I can do my regression based on my calculation. Based on, I've got my constant, that 22.16 or something to that effect. Okay, let's have a look. 22.618. So I've got 22.618 plus, then I've got my coefficient, which is 0.00005776 times time multiplied by time. And in this case, what is our time? Our time is our date converted into a value. Okay, so that means that and there's the formula, okay, which is the constant plus the time coefficient multiplied by time. And this is time converted into a value. You press enter and you just simply, remember, you anchor these two coefficients because it's linear. They're the same. The coefficients are linear, so the same. So you anchor them. Here we go. You anchor them and you simply just drop it down. And there, and you plot it. And voila. Now you have your time series, okay, as generated by Google Earth, okay, and we've generated our trend line as also generated by Google Earth. We've done everything in Excel. So this graph here is exactly the same as this graph here. It's the one that we've generated in Earth Engine using this code, using this script. Okay, so what we've done here with all this piece of code, okay, with all this thing, is we've generated a trend series from our time series, okay, and we've remodeled it in Excel. Okay, now this you can also generate in Excel by using, you go to data, and you go to data analysis, and you go to where it is, regression. Okay, so well, let's put it quickly. The input range, our Y, is our temperatures. Let's quickly do that. There's our temperatures, maximum temperatures, and then our input range is our time variables, and then it should, and then we're just gonna save it to another sheet, to a blank sheet, output range, and we're gonna constant, nope, we're gonna do, okay, let's just leave it as it is. We can put the residuals on, etc., etc. We press OK, and there it sits. And you can see, where's my constant? There's a constant, 22.618. What was our constant here? 22.618. And what was our time variable? 5.77 to the power of -5, which is exactly the same. So what we've done in Excel now with one click is this whole thing in Earth Engine. So what we've done here now is exactly what we've done in Excel. So we've got our time series, and just using the function within Excel, we've created our regression equation with our two variables, with our two coefficients, independent coefficients. And then they said exactly the same as in Earth Engine. So voila. What we've done in Earth Engine corresponds 100% to what we've now done in Excel. How was that? Not too shabby, huh? Not too bad at all. Okay, so interesting now. Let's quickly have a look and see. Remember, we've calculated now two coefficients. Let's go back here. We calculated a beta 0 coefficient, which is my constant, 22.618. Okay, and we've calculated a coefficient for my time. In this case, the coefficient for our time is 0.00005. Okay, so let's quickly go and have a look and see what we've done also on the image. Remember, we've calculated the linear trend image, which is this one here. This one here. Okay, so let's go to my inspector. Let's select any point here and see what happens. Okay, so we've selected that point. Okay, so now what's going to happen? Okay, so the temperature is 32.4. Remember, we've calculated the scale value of 0.0017 and an offset value of 25.85. Okay, now here's my coefficients. Okay, there's my coefficients. Remember, my coefficient for that specific point in my trend array is 25.825, which is the same as that. You can see there, it's the same. And my time is 0.018. Okay, so these two numbers here, you can see it's 25.82, and for our region of interest as a whole is 22.618. So that's quite different, not very similar. Okay, and then our coefficient for time is 0.001, so only 2 zeros, where our case it's 4 zeros. Okay, so our coefficient, this one here, and our beta 0 coefficient, our constant coefficient, and our time coefficient, you'll see there in our region of interest is quite different to our coefficients in our individual locations. And you see there's also a residual that it now has calculated for that specific location. Okay, but you can see the scale and the offset value is very similar, if not identical, to remember the 0 is my constant and the 1 is my time. So the 0 is 25 and the offset is my constant. So the offset and 0 is the same thing. Offset and constant is the same. 0 is constant. So offset, constant, or 0 is exactly or very similar. And the only difference between these two variables is really the residual. But you can see what we've done here, the regression equation, the linear trend that we've generated here for my region of interest as a whole, and per definition for my individual locations, are basically similar to what we've done here, is adding a trend line. It's exactly the same. Okay, so let's see what, if we go here, let's see what happens there. We'll see the temperature is 27.9. You can see there's the scale value, which is, remember again, the scale value is this thing here, that B1, or the coefficient, the time coefficient. And the offset is that value here, which is the constant. So that's the constant or the offset, and that is the scale of the time coefficient. Okay, so that should make sense. We go there, there's the coefficient. You'll see again 22.88, 22.9. Coefficient, time coefficient 0.0016, 0.0015. And here the residuals is 3.85. So between these two, it generates a regression function or a trend function for each of my locations, and then also for my region of interest as a whole. And I can use these numbers to calculate back in Excel to the original values. And therefore, if I can do that, I can use that two models to generate estimates for unknown future. Okay, understanding or based on the assumption that it's a linear function, that the trend will continue. As I said, these the scale and the time coefficient, these two values, indicates by how much will temperatures increase per month going forward. So that's what these two values is. Okay, and that's the 22 years your mean value, because remember this is mean reverting. Yeah, so interesting stuff. Okay, the beauty of this is, as I said, we've now exported the information and we've remodeled it or reworked it in Excel, which is quite neat. I think that was quite neat, and it basically, gives a little perspective on the code itself, what we're doing on the code itself. So when we talk about system this and that and this and that, what does it really do? As I said, the interesting thing is that it converts dates into numbers. Okay, and you can redo that in Excel. So that is quite interesting and quite nice to do. Okay, so this whole piece of code here, everything here, as I said, is basically what we've done in Excel. Okay, and also interesting, between these two sets of the trend, the linear trend and the regression, the coefficients are very similar, except so they are very similar. Okay, so let's quickly pause it for here. There's more to come. We're going to do a little bit more where we're going to generate a D-trend. Okay, we're going to remember, we're going to D-trend it so that we can get the seasonal pattern, because we know if we go into the data itself, we've already said there's a seasonal pattern here. Okay, there's a seasonal pattern here. So what we want to do is we want to subtract the two from one another. We want to take the numbers, okay, the observed values, is this one, or the observed values, and we want to subtract the trend. And that will give us our detrended values, meaning this part here. Okay, so if I take the observed values and I subtract the trend, I should get the sum of these two. Now, we're going to combine these two, the observed and the random, in Earth Engine. So if we take the observed and we subtract the trend, we should get the sum of these two, meaning we should get, you see the random is quite small, so what we're left with, if we make the 0, is that we only sit with the seasonal pattern. So that's what we're going to do here with this piece of code, but we'll get to that and we'll see what we're going to play around with that one. Okay, so for now, we've generated this linear trend function, and we've shown how it works in Excel and how it looks in Excel and how you can duplicate what we've done in Earth Engine in Excel and how they correspond. Great stuff. Okay, ladies and gents, thanks for joining me on this remote sensing journey. Appreciate it. Every day I learn something new. I must confess, this is not top of mind stuff. I'm not a boffin on these things, but as we do these things, we learn together, and that's the beauty of being on this journey. It's a journey of exploration of the unknown. It's also new to me, many of these things, but the beauty of this is as we move together, these things become understandable and easy to use, and it has far-ranging applications in our day-to-day lives, and hopefully this will help you in your projects, in your work environment, etc., etc. So good luck, stay tuned, much more to come. Please remember to like, subscribe, share, and I'll see you on the other side.